Has been a NASA physicist since 1960. He retired several years later. He was heavily involved with the Apollo program, which gets us to put a man on the moon. And so I would like to little known fact that I know he doesn't talk about. He's also senior tennis champion 6 times in the state of Texas. And nobody knows that, but I do. So I would like to introduce to you Mr. Don Cooper.
When NASA was given the job to put a man on the moon, they had to come up with the name of the project, and the name was Apollo. In 1961, President John F. Kennedy put this in a speech. I believe this nation should commit itself to achieving the goal before this decade is out. That would be before 1970, of putting a man on the moon and returning safely to the Earth. You know, this quote is usually cut off about 5 years. I guarantee you the astronauts paid attention to the last part. 6 years, almost 9 years later, Neil Armstrong sent the message from the moon. The Eagle has landed. Back in those days, 2 men were always known as leaders in rocket technology. First one was Robert Goddard, who did many experiments in Maryland. In 1932, he came up with the idea of using gyroscopes to control a rocket. The gyroscope is used in every rocket that's launched today. He also used liquid hydrogen and oxygen as the propellants because they were very high efficient and gave great thrust. They were used in the Saturn V to get us to the moon. In 1912, Werner von Braun was born in Germany. He read every paper that Goddard wrote and became very interested in rockets. When he got his PhD at age 22 and was appointed head of the German rocket program in Germany in 1940 during the Second World War. In 1960, after coming to the United States, he was appointed head of the Marshall Space Flight Center in Huntsville, Alabama, and was given the job to design and build the Saturn V rocket that would send astronauts to the moon. This is President John F. Kennedy visiting Huntsville last year. This is Werner von Braun. This is Lyndon Johnson, right behind Kennedy. When Kennedy ran for president, he didn't have enough delegates to get the Democratic nomination and was forced to take Johnson as his running mate, vice president. He hated Johnson. When I see this picture, I think, okay, Kennedy flew on Air Force One with Johnson, so if it went down, he wouldn't be president. This is Robert Goddard in the snow in Massachusetts with a little 3-foot rocket that he's sending up in another experiment. I was on vacation in Florida one time, and suddenly in a parking lot at a restaurant was the Redstone rocket that put our first man into space. The restaurant was closed. I couldn't ask him where it came from or why it was there. But I did do what was required of every person on vacation. Take a picture of your car. This is Huntsville, Alabama. There's a Saturn V that stands upright outside this 3-story building, which contains one that lays on its side. It's like a Johnson Center. This rocket is 363 feet tall. If you laid it on a football field, it wouldn't fit between the goalposts. Here are scale models. Here's the Mercury Redstone. Here's the Saturn V that went to the moon. Here's the Saturn V that put our first space station into orbit around the Earth. And there's the shuttle vehicle that went back and forth between Earth and space stations for 20 years. So what is Apollo? Project Apollo is lifting off from the Earth, going in orbit around the Earth, then blasting out of Earth orbit, coasting 3 days to the moon, going in orbit around the moon, going down to the surface, gathering up some rocks, putting down the American flag, putting down a scientific experiment, getting back in their vehicle, going back up into lunar orbit, blasting out of lunar orbit, 3 days back to the Earth, entering the atmosphere, parachutes come out, picked up by an aircraft carrier, and get on a jet airplane and fly back to Houston. That's a 7-day round trip for Apollo 11. But missions after this lasted longer because they stayed longer on the moon. Here's Apollo 11 lifting off away to the moon. You can see here the 5 largest rocket engines ever built. 1.5 million pounds each one. That gives you 5 of them give you 7.5 million pounds. The vehicle weighs 6 million pounds when it lifts off. Here's our first 3 astronauts: Michael Collins, Buzz Aldrin, Neil Armstrong. This is what I tell the kids. If you want to work in any scientific area, stay in school, get all the education you can. It doesn't happen like this guy, just walking around and suddenly finds himself on top of the world's tallest mountain. It's more like this. Robert Goddard, PhD in physics. Werner von Braun, PhD in physics. Neil Armstrong, master's degree in aerospace engineering. Michael Collins, West Point. Buzz Aldrin had a PhD from the Massachusetts Institute of Technology. These were all smart people, good physical condition, and that's why they were chosen as astronauts. So here's a lunar globe. Mountains here, mountains here. Here's a smooth plain. Here's the equator. Here was the site chosen as the first landing site for Apollo 11. The reason why it was chosen is that it's a place that you could get to using the minimum amount of fuel. You can appreciate that when you lift off from the Earth, there's no filling stations between here and there and back. So therefore, you didn't want to run out of rocket fuel, that's for sure. And so, very conservative, that was chosen. Plus, geologists saw some interesting rocks they wanted them to pick up. So why not? The lunar lander has 4 legs. The lunar lander is the vehicle that lands on the moon, and this is a model of it. You can see it has a rocket engine on the bottom here, and it has 2 windows, the little black windows here that look like a bug. And there's the steps where the astronauts get down to the surface of the moon. And this vehicle, on one of the legs is a plaque. And it's still on the moon right today. And the plaque, a picture of it is here. And first set foot upon from the planet Earth, first set foot upon the moon, July 1969. We came in peace for all mankind. It's signed by the 3 astronauts and Richard Nixon, who was President of the United States at that time. Someday, if China beaches the moon, they may buy that thing off and sell it on eBay. Every Apollo mission has a patch design. Here's Apollo 11. 12, 13, 14, 15, 16, 17. So 1, 2, 3, 4, 5, 6, 7. 7 times we tried to go to the moon. We made it 6 times. One time Apollo 13 had the explosion and had to come back before they reached the moon. Apollo 11 hatched. You can see here the Earth in the background. This is the lunar surface. And there's an eagle landing on the moon. The astronauts named their vehicles. Neil Armstrong named the lunar lander the Eagle. And he radioed back, the Eagle has landed. Every one of us that were glued to our black and white TVs knew what that meant. So how do we get to orbit? Well, we lift off. First stage gets us up about 50 miles. Second stage gets us up close to 100 miles. And then the third stage, we have to pick up another 3,000 or 4,000 feet per second to get us up to 25,000 feet per second. So we'll stay in a 100-mile circular orbit around the Earth. It takes 12 minutes to do this. Every rocket that goes to Earth orbit follows a path very close to this. And the reason why is because this is the path that uses the least amount of fuel. And then, once we're in Earth orbit and we want to go to the moon, we have to increase our speed another 10,000 feet per second in order to escape the Earth's gravitational field and head into outer space. So we leave the Earth's orbit traveling at 7 miles per second. This is a nice rocket going into orbit. You can see what it actually looks like as it starts to go up and then go into circular orbit or whatever kind of orbit it's going to go into. Now, one of the things about rockets is that as they accelerate through the atmosphere, they encounter what's called dynamic pressure. Put your hand out the window of a car, you can feel the air press against it. The faster you go, the harder it presses. This force becomes very great as a rocket accelerates a lot and builds up speed until there's a point where there's a maximum dynamic pressure. Now the vehicle cannot rotate while it's going through that. If it did, the forces would be so great it would probably break it in half. So it stops rotating and goes straight up for a period of time and then starts tilt again. If you happen to notice, one time on TV I heard them talk about SpaceX going into orbit, and I heard the commentators say, we have passed maximum Q. Q is the symbol for dynamic pressure. And those of us that worked in space knew exactly what that meant. I don't know if you caught it or not. I was impressed that the commentator even knew what Q was. So, at the same time, when we're gaining velocity, we go through the speed of sound pretty quickly, and then we continue on up with more and more speed as we head towards orbit. And acceleration is when you're sitting in your car, you're getting ready to take a drink, the driver takes off, liquid goes up the cup, into your mouth and out your nose. That's called acceleration. Rockets have a lot of acceleration as they go up. They run out of fuel in the first stage, acceleration goes to 0. Second stage, acceleration goes to 0. And finally, the third stage gets us into orbit. The astronauts always comment about how much vibration there is in the first stage compared to the second and third. And that's absolutely true. The big F1 engines that produce 1.5 million pounds of thrust vibrate a whole lot. Buzz Aldrin commented his eyes were focused on the abort button the whole time. The first stage was burning. Okay, so with that, we are ready to go to the moon. And this is our rocket. That's the first time I've managed to do that. Now,
10, 9, 8, ignition sequence start. 5, 4, 3, 2, 1, 0. Launch commit. Liftoff. We have liftoff.
and we're on our way, and we have those 5 big rocket engines on the bottom pushing us out. In about 2.5 minutes.
Hold it.
After about 2.5 minutes, we run out of fuel. We've been burning fuel at 30,000 pounds per second. So we've run out of fuel in the first stage. If you've noticed railroad tank cars going down the railroad track, it takes 42 railroad cars full of propellants to fill up this first stage. So now we have the second stage that has 5 more smaller rocket engines that fires up and starts pushing us higher and faster until we run out of fuel in this stage and it goes into the Indian Ocean, just like the first stage did. There's nothing reused in the Saturn program. And then we end up with a rocket that has 1 rocket engine that pushes us on into Earth orbit. And now we're in Earth orbit, going around the Earth in this configuration. And then we fire this rocket again at the right time that pushes us out into space. And as soon as we get going towards the moon in space, the service modules, what this is called, disconnects like this. And the astronauts live in the top, this little cone here, which is where they live with the asbestos bottom. And it's a cone that the 3 astronauts are in. And now we have the astronauts, we have the service module with this rocket, and we have what's called the S4B stage, which is the 3rd stage of the Saturn V. And we seem to be missing something. I think it's called the lunar lander. Where is it? Well, this is what happens. And the astronauts turn around and rendezvous with the lunar lander, connect to it, and pull it out of the upper stage of the Saturn, just like that. This goes on into outer space. And so now we're traveling through the moon, towards the moon, with the lunar lander here, connected to the command module, connected to the service module. When we get closer to the moon, this rocket engine fires again and slows us down and puts us in lunar orbit. And then Neil Armstrong and Buzz Aldrin crawl through the tunnel at the top of the command module into the lunar lander and disconnect. Comet stays in orbit around the moon. And now, suppose the surface of the moon is the table. And with the table, the astronauts now have slowed down. They're getting closer to the surface of the moon, and they're going to land somewhere like down here. They come out from behind the moon. I'm going to switch to the bigger model at this point. They come out behind the moon, laying on their back. They're standing up. There are no seats on the lunar lander. They come out behind the moon like this with the windows, the 2 windows here pointed straight up towards the stars. And they're coming across the lunar surface like this. And they cannot see the moon. All they're looking at is the stars. At the same time, they're slowing down as this engine is firing, slowing them down horizontally. And then the lunar gravity is pulling them down closer to the surface. And they're headed down to crash into the moon without ever seeing it. However, the guidance equations, which have been controlling this vehicle the whole time, at about 10,000 feet off the surface, they do a pitch-up maneuver like this. And suddenly Armstrong can see the moon and the landing site. Now, what this looks like, so the question is, how does he, and he looks and he says, holy cow, look at all those rocks. It's supposed to be smooth down here, but it's not. The guidance equations are going to land right in the middle of a crater and some big rocks as big as cars. And obviously that is not going to work. Well, I know it's hard to believe in 1960 we didn't win it with a joystick. He had his hand on it. And what he could do is change where the landing site is going to be. And I'm going to draw this and then I'll explain. On the window that he's looking out of, I draw these crosshairs. If he clicks, 2 clicks to the right, it tells the guidance equations to change the landing site to here. If he clicks 1 down, it lands shorter here. What he does, he looks at the situation and says, I can see beyond the crater that it's smooth over there, so he redesignates 3 clicks downrange, and the guidance equations then take over, fly over the crater, the rocks, into a smooth area that he can land in. Now, whenever he does this click here, the control system also adjusts the attitude of the lunar lander to change the crosshairs to show him exactly where he's going to land. Now you might say, well, how do we know that these crosshairs really represent what Armstrong is looking at? You're going to tell me that NASA didn't know exactly how tall he was when they drew this on the window. But it was made for him. Okay, Buzz Aldrin is in the right-hand side of this vehicle, the lunar lander, and they're coming down like this toward the surface. And there's 2 radars. There's one that's called long-range radar that tells them when they're fairly high, and the other one's short-range when they get closer to the moon. It's more accurate. There's actually a 3rd radar that's pointed up towards Collins as he flies over in the upper orbit around the moon. In case they have to do an abort and go back up into orbit, it requires Collins, and they do a rendezvous in lunar orbit. But they're on the way down to the surface of the moon. And I have here a recording of Buzz Aldrin talking to Neil Armstrong. And what Buzz Aldrin's job is, let me get this. 1 second, here we go. It's Buzz Aldrin's job to tell Armstrong how high they are, how fast they're going down, like 3.5 feet per second, 47 feet per second forward, so that Armstrong can concentrate on looking out the window. Now, he can also control within about 10% the thrust of the descent engine. So he can slow down the descent or speed up the descent and actually redesignate and land at a different place so he so choose. So that's what he's concentrating on, at the same time listening to Buzz Aldrin telling him what the computer is saying, so that he'll have that guidance to be able to do that. So here we're starting down. Well, that's really good news. We're running into the descent. We have a 1201 alarm. Armstrong and Buzz Aldrin did not know what that meant. Neither did nearly all of mission control. There was one person in mission control that knew what it meant. They were a representative from MIT that developed the equations. And what happens is that every 2 seconds, the guidance equations take into account the altitude, the velocity, the landing site, and issue the commands to control this vehicle. If they cannot get that job done in 2 seconds, they throw away non-important data and restart the computer and try again. If this continues, they will not be able to land on the moon. They will have to abort and go back to commas. The worst case, if they continue and it continues to not get a solution, they will crash into the moon and kill themselves. So you can see it's a very serious situation that nobody expected to have happen. So mission control makes a real quick decision. Well, let's go for a while and see what happens. Mission control thinks everything is under control.
Roger, 1202, we copy it. 35 degrees. 35 degrees. 750, 723. 700 feet, 21 down. 33 degrees. 50 down, 2.5. 19 forward. 30 on the right. Yeah, down. 20 feet. 13 forward.
And you notice it does bother, it's 4.5 down, 5.5 down. That's 4.5 feet per second, 5.5 feet per second. The objective is to land less than 3.5 feet per second with all 4 legs coming down on the moon at the same time. Now also you'll notice that fuel's very short here, 60 seconds, which means they have 60 seconds of fuel left. They either have to land or abort and go back up into orbit. And then they have 30 seconds of fuel left. Contact light means that there were 3 ropes, light ropes that are contact. They're about 6 feet long, hang down from 3 of the legs on the lunar lander. Any one of them touches the surface of the moon, a light comes on right in front of Buzz Aldrin. That means press a button and turn off the descent engine. The vehicle is going to land. So that's what that means. And that was the voice of Neil Armstrong announcing that they had successfully landed on the moon. Now they get out. They get out. Buzz Aldrin is here. He has pulled out a seismic sensing device out of the cargo bag and put it on the moon. American flag is in the background there on the left. And they pick up about 90 pounds of rock. They climb back into the lunar lander. And now, at the right time, they launch to go back up into orbit. Now, The lunar lander is actually two vehicles. There's the one that landed with its rocket engine, but the upper part of it separates like this and goes into orbit with this rocket engine and leaves this as the launch pad on the moon. And this is the one that has the plaque on it that still stays on the moon today. And here they are, and they're going back up toward orbit. And by the power of mathematics, who comes along exactly at the right time? Michael College. And they were glad to see Michael College because this was their ride home. They dock, they crawl back through the tunnel into the command module here, and then they don't need the lunar ascent anymore. They discard it crashes into the moon. And now we have this vehicle in orbit around the moon. This fires, pushes them out of lunar orbit, and then after a while they don't need it anymore. It's discarded. And now what's left is this little column where the three astronauts live, with asbestos on the bottom, that's going to protect them from the heat when they re-enter the Earth's atmosphere at 7 miles per second back from the moon. Now, if they come into the Earth's atmosphere at too steep an angle, they will burn up and die. If they come in too shallow, then they will skip out of the atmosphere, go up for a ways, Earth's gravity will pull them back, and then they burn up and die. So it's important to get the right angle at re-entry. Have any of y'all ever heard of Poppy Northcutt? I worked next to her in 1961 in the parking lot of TRW. A very cold winter in Houston. We almost froze. It was very, very cold. She was the first woman in mission control. She monitored the angle that they came in re-entry to come back to the Earth. She had just graduated from the University of Texas, 3.5 years math major, flaming liberal woman. I was petrified of her. I didn't know what to make of her. But we didn't disagree on anything. It was just, we sat next to the door, we both froze pretty good. Our boss next door, it was well known, he had a bottle of Jack Daniels in his desk. And it seemed like Poppy would go over there twice a day for some reason. And we all thought she was just getting a little warmer, you know. 65 years later, I was at the Jewish Community Center playing tennis, and I saw a notice that Poppy was going to come talk. I thought, I'll go see what Poppy's doing, because I always wanted to ask her that question about Jack Daniels. So here I am heading down the hall, and I'm thinking, I don't know why I'm doing this. She probably didn't even remember me. And not only that, this is a women's group. Nobody invited me. And so I thought, well, why not? I'm already here. Suddenly I heard this voice, Don, I never see somebody else in the old trailer. We had a good time. Somebody took her. I had my camera and they took my picture. Women didn't know what to make of me. I was the only man in the audience. And but it was a fun time to see Poppy again. She was on TV quite a bit during the 50-year anniversary of Apollo 13. You look like you had heard of her. Yeah, she went on to get her law degree. She worked for the mayor, and was involved in a lot of politics in Houston. So, that's how, and now we enter the Earth's atmosphere. We come down, open our parachutes, frogmen come out, take the astronauts out, put them on the aircraft carrier back to Houston. And that's how we went to the moon and back in 1969. So, a number of years, not they have this mock-up of the lunar lander. And here's the fence. And you know that thing wasn't really that high, and I really want to get my picture standing on the pad. There was a, I thought I totally got away with it when a tour group showed up, and the leader of the group just kind of looked at me and laughed. It was funny. The building that had the Saturn V, there was a young gal at the entrance to answer any questions. And so I walked up and I said, is everything in this building Saturn V, Apollo stuff? She said, oh yeah. She said, this building is really popular among the slow guys. Thanks a lot. So, what I just told you is what I tell school kids. For the last 18 years, I've gone around the Houston area and spoke to school kids about how we went to the moon and back to encourage them to study math and science. I hope I've influenced a few of them. I used to speak to about 2,000 a year, but since COVID, it hasn't picked up all that great. But I'm still going at it. If I could answer any question, I would.
Mr. Cooper, I didn't get any clarity on your role in the lunar efforts, the building of the Saturn rockets. So what was your exact role?
Okay. I work as a mathematician for NASA. Just a moment. When I was in Huntsville, Alabama, worked for the Marshall Space Flight Center and a group that developed the guidance equation for the Saturn V. And this is a picture of a problem. A guy named Gene Smith had developed the ascent guidance equations to go into orbit. But the problem is this: at the right time, the third stage of the Saturn V had to fire out of Earth orbit here and be pointed in the right direction, such that 3 days later you end up 10,000 kilometers in front of the leading edge of the moon. Now, the Earth is going around the sun, we're going around the orbit, and Earth. The moon is going around the Earth. What direction should this vehicle be pointed when it cuts off in order to accomplish 3 days later being right there where it's supposed to be? How would you solve that problem? My boss, my supervisor, was a woman. She was a good mathematician, George Chandler. She called me in her office in 1963 and said, I want you to work on that problem. I didn't have a clue, not a clue. What I didn't know, and didn't find out for another 60 years or so, is that NASA had given a contract to 3 universities to solve this problem. They had spent almost a year and came up with 0. And suddenly, a physics major, 2 years out of Oklahoma Baptist University, I did have enough math for a major also, was supposed to solve this problem. Have you ever heard the phrase, Hail Mary? That was me. Well, first thing I did was go to the library. I found one article written by a guy out at Jet Propulsion Laboratory, so I got on an airplane, flew out there and talked to him. He goes, I don't know how to go to the moon. We don't go to the moon. We go to the stars. We go to the planets. We never thought about going to the moon. Well, I didn't learn anything from him. So I came back, still didn't have a clue. Years before, I found a book on how to solve. It was a book on how to solve math problems. And what it said was, if you can't solve the problem you're working on, think up a simpler problem and solve that one. While you're doing that, you'll get an idea about how to solve a more difficult one. Well, I've applied this several times, and what I did, I applied the same thing on this problem. And what I did simpler was to develop a couple of simulations that I knew I would need if I ever discovered how to calculate the direction to fly, which I still had no clue after a year. I worked on and thought about this for a year, and why Doris Chandler stayed with me, I have no idea. I mean, she must have been asleep or hibernating or something, because who would send somebody for a whole year that still didn't have a clue how to solve a problem? But I was working on it. I was thinking. One day coming back from lunch, I saw a poster across the hall from a group that had been studying trajectories going to the moon. And it was this ellipsoid that had a bunch of lines on it. And I asked the guy, I said, what is that? He goes, those are all the possible paths going to the moon. And I said, well, what are all those lines? And he said, that's different launch azimuths. Now, a launch azimuth, when a rocket is sitting on the path and it gets ready to launch, it's going to tilt over in a certain direction. That direction is measured from true north. And for Saturn V, for the Apollo mission, that was from like 72 degrees to 105. So as the launch window progresses through 4 hours, every second the angle that it misses over is going to change. And that angle was represented by a line on that ellipsoid. Almost yelled Eureka. I ran back to my office. That's what Archimedes did when he was sitting in the bathtub. But it just instantaneously came to my brain how to calculate the direction. All I had to do was to calculate a vector that was tangent to the ellipsoid, and it would go to the moon. It was just as simple as that. The year before, I had taken a course in vector and tensor analysis at the University of Texas, and so, University of Alabama there in Huntsville. And so I was well acquainted with vectors and how to manipulate them. But and so I was ready for that solution, and that's what ended up. If you want to see my paper, put in F. Don Cooper, NASA, something like that. You'll find it pretty quick. It's on the internet. It's on the NASA archives, 1965, and it shows all the analysis and how I analyzed and proved that it would work. It was accepted by NASA. It was programmed into the onboard computer and flew every lunar mission. And that was my small contribution. Apollo 13, they called me at midnight to get the mission control. And I was the first one there in the parking lot. We never called it mission control. It was building 30. And so they wanted to know how to calculate the warrants. Well, a couple of years before, Johnson had contracted out to the Massachusetts Institute of Technology to write the equations in the command module, which included the abort going to the moon. And so Johnson suddenly realized that they had not verified that what MIT did would really work. So they turned to TRW, who I worked for, and said, we want you guys to verify that what MIT did was correct. So somebody got the bright idea that I should be the project manager. And I said, okay, but I get to choose the people. I chose 6 people smarter than me. We spent 2 years, and we analyzed every guidance phase of the Apollo mission, including abort. So when they called me to mission control and wanted to know how to do the abort, they gave me the coordinates of where the vehicle was and how fast it was going. And Dave McCabe, who was the expert on that analyst, and he found an old key punch machine in the closet that had dust on it. We dusted it off, punched the cards, ran across to the comp lab, did the computation, and handed it to mission control. An hour later, they asked for a new solution, which we gave them also. It took MIT an hour to battle through the snow. They had no one standing by in Massachusetts. The second calculation agreed with them, and so everybody felt a little better about the solution. However, it was too late to do an abort. The moon gravity was already pulling the vehicle towards the moon. It was picking up speed, and there were too many uncertainties. And the decision was made to let it go around the moon. The moon's gravity pulled it around the moon, and it started back to the Earth. And any of y'all that have seen Apollo 13 movie, you can see all the different problems that happened. And that was Apollo 13. And my analysis of that is, go ahead. The Apollo 13 astronauts were saved by thousands of nerds. We were invited to parties. Everybody wanted to hear what we had to say. This actually happened to me. That's what inspired me to write this. All because we studied math in school. The Apollo operations team, which I was a small part of, we were all awarded Presidential Medal of Freedom. So, that's what you were asking, I think.
It was.
Well, I tell you, it was a lot of fun. You know, the group that I was in that did the guidance equations, Gene Smith was, he was 24, no, he was, take it back. I was 20, I was 23. Wayne Beaton, my doubles partner in tennis, was 24. He did the performance analysis for the Saturn V guidance equation. The oldest guy in the group was Gene Smith, who was 28. You know, he was really old. And then Doris Chandler, we never asked her inquired about her age. she might have been 30 or 29 or something like that. But, you know, we never thought of her being old. We actually, I don't remember anybody ever saying she's a woman. I mean, we know that. We just never talked about it. She was a great supervisor. She's a very knowledgeable mathematician. She helped us when we had a problem. She assigned us things to do and let us go. And at our age, you might wonder, and I've wondered this before, why did anybody think that we could accomplish this task that we were given? I can only say that the Marshall Space Flight Center was run by the Germans, who developed the V-2 rocket in Germany in 1940. Our second level boss was 22 when he designed the control system for the V-2. The Germans did what we did when they were in their 20s. They were not afraid of young people. They were not afraid to give us tasks and let us work on them. They assumed that we would accomplish what we were supposed to do. Now, had we had American supervisors in their 30s and 40s, they would have probably never given us the task that we had. We were too inexperienced to do that. So I would say to young people, don't underestimate yourself. Learn all you can. Stay as skilled as long as you can. Get the best education you can. And opportunities will open up that you don't even imagine. We're going to have self-driving cars pretty soon. You know, artificial intelligence is going to be here. Security, sending messages and things on the internet already is very important. It's going to become more important. There's things that we can't even think of that's going to happen in the future. And it's going to be up to you to solve the problem. It's not going to be old guys like me. Oh, third graders always ask, how old am I? I'm 87.
So there were so many unknowns for this whole space program when it started in 1960. How in the world did Kennedy successfully estimate the achievement in 10 years? How did he come up with the number 10?
Lyndon Johnson. When he assigned Lyndon Johnson to obscurity on the Space Committee, he started talking to all these rocket scientists, Werner von Braun, you know, people from Langley, people that worked with rockets, and they started telling him about how we could go to the moon, and they started telling him how we could do it, although it wasn't totally decided at the time, but they all had a different theory somewhat of how to go about it. But that's where the knowledge came from, Lyndon Johnson. And he got Kennedy to put that in his speech. If you look at that speech, and nobody ever does, Kennedy listed about 6 things. The other 5 are totally forgotten. What got everybody excited was going to the moon. And the reason why he made that speech in Texas, by the way, is Johnson told him he was going to lose the next election if he didn't get down to Texas.
What made you, or what got you into NASA? What made you go to NASA? What made you go to NASA as like your career?
How did I end up at NASA? Well, actually, when I graduated from college, I got a letter from the Army that said, come down and take a test to see if you're qualified to be a private in the U.S. Army. I passed the test, and they told me 2 weeks after graduation I'd be drafted. The Vietnam War was starting out pretty good, and they needed lots of us young people to send over there, so I was going to go to Vietnam. When I walked out of the out of the Army building there in Oklahoma City, I saw this big sign that said Air Force. I thought, well, I'll check with them. So I go down and ask them, you know, were they interested? Well, they really were. And they sent me out to Tinker Air Force Base, and I spent 2.5 days taking tests to go to Officer Kennedy School in the Air Force. And so that's what I decided would be better than being drafted. So that was my plan. At the start of my senior year in college, I went to pick up a guy at Lake Dennis, and he was filling out this application for employment for the federal government. He had an extra form, and I just filled one out too while I was sitting around watching him. I didn't even take it. I just left it. Turns out he mailed both of them. And so they went into the hopper. 2 weeks before graduation, I got a note in my mailbox, call so-and-so. And it was this long-distance phone number. We had one phone. It was a payphone in the basement, 400 boys in the dorm. We had one phone. I'd never made a long-distance call. I didn't have money to put in a payphone. I had 25 cents total. It was the money, all the money I had. So I didn't do anything. A few days later, somebody came running in my room and said, somebody's waiting for you on the phone in the basement. I go down there and I said, hello, and he goes, whenever you can call me back. I said, who are you? I'm Al Bromley from the Army Ballistic Missile Agency in Huntsville, Alabama. I want you to come to work for me. And so I said, well, I can't do that. I'm gonna be drafted by the Army or I'm going in the Air Force. He said, come to work for me, I'll get you out of both of them. That sounded pretty good. 2 days after graduation, I was in my car driving to Huntsville, Alabama. I worked for the Army for 1 year. During that time, I joined the Huntsville tennis team. My doubles partner was Wayne Deaton that worked for Doris Chandler. And one day he says, how would you like to work for NASA? I said, it sounds good to me. And so 2 weeks later, after I interviewed with Doris Chandler a couple of days later, 2 weeks after I said, sounds good, I was working for NASA. This was on Redstone Arsenal, Huntsville, Alabama. Redstone Arsenal is a plot of land about 10 miles wide, 20 miles long. It's an Army base, completely run by the Army. And it was the location of the Army Ballistic Missile Agency, which was headed up by Von Braun, the guy I just mentioned, rocket guy. On July 1960, him and 6,000 other employees were transferred from the Army to NASA. And that's what created the NASA Center in Huntsville, Alabama. It was the largest NASA center. It still is the largest NASA center. And we excelled in rockets. If you want to see rockets, go to Huntsville. So that's how I ended up at NASA. And the reason why that I was so willing to do that is because in my job at the Army, we were designing a new missile. And I was the lead mathematician in the group. And I was given the assignment to develop firing tables for the new missile and for a new mortar. And firing tables are written so that people in the Army can know how to either kill the most number of people, destroy tanks, destroy reinforced buildings, destroy frame buildings, whatever mission is going to be there. And I had already decided I didn't want to spend the rest of my life doing that. So I was more than willing to get in with the Apollo program rather than stay with the Army. I could have worked for the Army probably the rest of my life. And it's not that that's not a necessary thing. That's what the Army does. But I just didn't want to do that forever. Sometimes young people are surprised at the job of the Army is to kill people. Yeah, the number one reason that boys volunteer for the Marines is to blow things up. Yeah, a lot of planning went into things I did back in those days. It's probably about like your life. Although I didn't know what a counselor was. We just flew by the seat of our pants. Well, thank you all. I enjoyed it. Always enjoy it. I know we don't have a lot of students here, but I always enjoy talking to kids. I hope I influence a few of them to make good decisions.